Hello and welcome to lesson 1 of week 6. In this lesson, we are going to talk about linked list and we'll look at the implementation in Python. My name is Mildred. Now, a linked list is a linear data structure in which the elements, which are called nodes, are connected using pointers, which are also called references. Each node will store the data and a reference to the next node in the sequence. And so when we look at arrays or lists in Python, we don't have random storage of items. We have all of the items or the elements of an array stored right next to each other in memory locations. So when you come to index position 0, index position 1 has the next, 2 has the next. But this is not the case with a linked list. It doesn't store item like that. It just stores wherever there is free space in memory during the insertion and deletion. And why this is better than arrays is that when you remove or when you delete something, it doesn't have to shift or move from places. It just remains in the same position, and what you have is a pointer to the next. So the first node in a linked list, we call it the head, and the last we call the tail. So why do we want to use linked lists instead of arrays? While arrays have fixed or resizable blocks of memory, linked list has dynamic memory allocation. Array is slow for insertion and deletion operation, and linked list is fast for insertion and deletion, especially when the position is known. Random access is possible for array. Random access is not possible for a linked list. We need to traverse through the list. So when do we use linked lists? When we want to have frequent insertions and deletions. When we want to allocate memory dynamically, we use a linked list. So the structure is to have a data, and then that data has a pointer to the next item. And if there is no item next, it just has points to none, something like that. So we have different types of linked lists. The first one we are going to look at is the singly linked list, written singly linked list. In this type of linked list, each node links to the next node. So let's focus on the implementation of the singly linked list, and then we'll look at the doubly linked list and the circular linked list in another lesson. For the singly linked list, we know that we want to have a node, right? And this node has a pointer to the next item. We want to think about how to implement this so that we always have a blueprint for the node and have a blueprint for the linked list, and we can create several methods for the different things that we want to do. We might want to have a method that displays the list, a method that performs insert operations in different positions of the list. We might want to have a method that deletes a node or traverse through the list or search the list, and several other methods as much as the functionalities that you want. So the first thing I will do is to define the node. So let's use object-oriented programming for this. Let's say class node, and we want to have the node having the data and the pointer to the next. So we'll have def init self, and we want the data. So we're going to say self.data is equal to the data, and now we have the pointer self dot, so we use next, and this next will point to none. So we just having an empty node. There's just one that points to nothing. So now we have the node class that we'll use in our linked list. Let's create a class for the linked list. Let's say class linked list. Now we want to define the init method. We'll just say self. We're not collecting any parameters here. And we want to define the head. We said that the first item is the head and the last is the tail, right? So let's get an empty list. So let's say the first item is none. So let's say self.head is equal to none, like this. So this will initialize an empty list. What we want to do now is to have methods that we'll use to put items in this list. Let's say we want a method that will, let's say, display the list if we have items in them. So now we're just creating a class, and then we use objects to create instance of this class or to have different items from this class. I will have a method called display, and whenever you don't have any parameter, you just use only self. And for display, I want to get the current node, right? So the current item will be equal to self.head, which is the first one. Now we want to say while there is a current item, let's print. That's for display. Let's say we print current.data. So now we want to define what this data is, right? We want to get the data, and we want to put also the pointer, and the end of it will be equal to, let's put a pointer. So what we are doing here is to have a method that when we call will display all of the items in the list. So we want to loop through that list, and we want to get the current data, and we want to append this arrow to say this is the pointer to the next, right? Something like this. Then now we'll just update what the current is, current.next. There are many ways you can implement this. There are many ways you can think about this. And if there is nothing, you just print none. Okay, let's print none like this. So it points to none. So this is one method. It's not necessary you have that, but I'm trying to show you that when you implement the linked list, you want to think about the method you want to have for the list. Now we have a method that displays what we have have there? We have an empty list, we don't have anything yet. Let's create a method that will allow us to insert in different positions. We can allow it to insert at the end of the list, we can allow it to insert at the beginning or at a particular position that we want. Let's say we want to insert at the beginning, for instance. Let's say dev insert at beginning. So we want to insert the data at the beginning, and what we're inserting is going to be a new node. So we know that the element is called a node, right? So we'll say we're inserting a new node, and the new node is equal to, so we want to create an instance of the node class, so we'll say node. So we have the new node is going to be inserted at the beginning, and let's say new node dot next is equal to, the next now is going to be self dot head, and self dot head will be equal to new node. We inserted data at the beginning, and so we want this new one that is at the beginning to become the head, because we say the first element or the first item is the head. The first node is the head. So now we want to change that next item. When it goes to the beginning, the one that was at the beginning is moved to the next, and that next item is going to be what the previous head was, and the new head will now be the new node. So you can think about this in a different way. What if we say we want to have another method that will insert it at the end instead? So let's say the insert. So you don't need to have all these methods. I'm just trying to show you how we implement this in different ways. You think about what you want to implement, what method you want to have. You can just have the linked list method that will insert, traverse through, delete, and things like that. But let's see that we want to insert at the end. Let's put insert at the end, and at the end of this we want to, it's going to be similar to this, but we are inserting it at the end instead of at the beginning, right? So we'll say the new node will now be equal to node data. So we're using the class node here to define that. So new node is equal to node data, and if self.head, so we want to check if there is no head. If self.head is equal to none, then whatever we insert, so if it's empty, whatever we insert is the head. So self.head is equal to new node, and then you return. But if there is already a head, you want to get the current should be equal to self.head, and you want to now loop through. Let's say while current, so you're looping through. So we'll say while current.next, we want to say the current is equal to current.next, and current.next is equal to new node. So this will insert at the end. So we create a new node, we check if self.head is none. So if there is no head, we want to make the new node the head, and then we just return. But if not, if this condition is not true, this if block is not handled, we want to say the current is going to be the head, right? And so we want to loop through the next. So while current.next, so as long as there is a still item in the list, right, we want to assign current is equal to current.next. You always want to update the current one to be the next item as it iterates through it, and then you want to say current.next now at the end is equal to new node. So current.next is equal to new node. So when you keep looping through like this, and when it gets to the end, you want to now get the next one will be the new node, which is the last part of it. So we can also do like we want to insert after a particular node. Let's say dev insert, let's just call it insert after. So like I said earlier, you don't need to have all of this, but you can have it to say you can call any of these methods to insert at the beginning, at the end, at a particular location. So let's use this method to say insert after. We have self, we want to get, so if you want to insert after, you want to get the previous data, and you want to get the data you want to insert. Now you know that the current is equal to self.head. We're starting from the beginning. So while current and current.data is not equal to the previous data, we want to say the current will be equal to the next. And if, let's say, if not current.next, or let's say if not current first, because we say if not current, we want to say the previous node is not found, right? We are looking for the previous data, and we want to start from the beginning. We want to say while we have the beginning and the current data is not equal to the previous data, we want to say current equal to next. This is just like looping through from beginning until we find that previous data. And if we don't have current, we want to say previous, let's print previous node not found, right? And then you just return. So after this, if this is not the case, you want to get your new node is equal to node and the data. The next item that is pointed to will be equal to current.next, and the current.next will be equal to the new node. So what we've done here is to locate that this previous data is to locate a record that is there and we want to insert where the previous record is, right? And we're going to start from the beginning and we're going to loop through to go to the next. And every time we try to loop through, whenever we don't have a pointer to the current or we don't get the previous data, we want to say the previous node not found for us to insert into it. And if this is not the case, it ignores this whole statement and now starts with the new node dot next will be equal to current dot next, and the current dot next will be equal to new node. And let's see how this works as we go. When we do a test, we'll see whether this works well. So we have 3 different inserts at different positions. You can have just an insert or have just one method that you select where you want the insert to be, at the beginning, at the end, any position at all. Let's do one for deleting. Let's say def delete node. So let's put a key so we'll know what node we are deleting, right? So let's say key. Now we want to get the current, which is going to be the first one, the head, self.head. And we want to see if the head node itself holds the key. So we say if current and current.data is equal to the key, we want to say let the head, so let's say self.head is equal to the next. And so we want the head to point to the next and we want the current to point to none, right? And then we return. Now if this is not the case, we want to search for the key, right? Because if the current and the current data is equal to the key, we want to set the head to the next and we want the current now to be equal to none. We're deleting that. But if that is not the case, let's get previous is equal to none and let's say while the current, so we want to loop through this. While that current one is not equal to the key, we want to set the previous to the current and then the current to the next. And then we have the condition for if not current, we want to say the node is not found, and if not, we want to have the previous dot next will be equal to current dot next, something like that. I'm trying to think through it. So say while current and current dot data is not equal to the key, we want to say the previous is equal to the current and the current is equal to current dot next. I think this is what we should have. And let's say if not current, we want to say the node is not found, right? Node not found. And when it's not found, just return, maybe something like this. And we want to now say that the previous dot next is equal to, so when we delete a particular item, that will be equal to current dot next. And we want to set the current to be equal to none. I think this will do it. I'm not sure, but now we have this class. I think we should test this before we go further to make sure that what we are doing actually works. So let's say if name is equal to main, so we want to create an object. So let's call this linked list is equal to, we want to instantiate this class linked list. Now we are not passing any parameter here because it's just cell. All right, so we have the object now called linked list here. We want to insert, let's say we insert at the end. Let's say linked list dot insert at the end. Let's insert 10 at the end, right? Let's insert something else at the end, dot insert at end. Let's insert 20 at the end. So we have 10, 20. Let's insert at the beginning 5. So we should have the structure to be 5, 10, 20 because we put 5 at the beginning. We first put 10 at the end. So let's visualize this. Let's say we have the list. We put 10 at the end and then we inserted something else at the end and then we inserted something at the beginning. So we should have it like 5, 10, 20 like this. And let's say we want to insert, let's look at insert after. So we want to put the previous and the data we want to insert. So we want to insert after 10, we want to insert 15. So let's say li dot insert after, we put the previous here, which is 10. Let's put 10, and we want to insert 15 after 10. So we have a method here to display this, and we want to print out the current data and the pointer to the next. So we'll say ll.display. So we want this to display, and we'll have the output 5, 10, 15, 20, and then points to none as the end. Let's run this and see. Yeah, that's what we have. So everything works well regarding the inserts and the display. Now let's see if the delete node works. Let's say we want to delete 15. So we can have 5, 10, and 20. Let's say ll.delete node, and the node we want to delete is 15, right? And then after deleting, we want to display. So we have 5, 10, 20 because 15 is out and it points to none. So the display method we created here will always print the current data, and the end is going to be the pointer to the next. And then we'll have the current is equal to current.next. And whenever we don't have any more in that loop, you want to put none as the pointer. And that's why we have it like that. And so we can display and visualize how our linked list look like. Okay, so you can think about different methods that you want to use. We can have a method that we use to traverse through the list, and That is, we want to visit each of the node and access the data that it has. Let's try that so you can see the endless possibilities of this. So let's say we want to have a method that we'll use to, let's call this traverse. I want to traverse through this list. So say traverse self, and we want to get the current, which is the head. So current is equal to self.head, and we want to loop through to print the current data in every iteration of the loop, right? So say while current, we want to print the full data, current dot data, right? And then point to the next, current is equal to current dot next. So we have this as the traverse method. And so when we want to traverse, we can now say, let's go back to our example here and say linked list dot traverse. So it should just give us the output 5, 10, 20. It's not going to display with the arrows like this. Maybe just give us the data. So 5, 10, 20. So we can see how it outputs it here. Now let's do another, like let's say we want to implement a search in this. Let's say def search here, and here we are going to have the targets that we're searching, or the key. You can implement this search in different ways, but we're going to use a simple linear search that we have learned in the last lesson. Let's say current is equal to self.head. We want to say while current, we want to check if the current data is equal to the key. So if current dot data is equal to key, we want to return true, and if it's not, we want to go to the next. So current is equal to current dot next until we get to the end. All right, so if is equal to the key, you return true, and if it's not the case, the current will now be equal to current dot next, and if you get to the end and you don't find it, you just return false. And so let's search for 15, for instance. We know we deleted 15 already. So let's say the variable found, I'll run this. Let me clear here so we can see. I'll run this, and we have all of this. So now I want to have a variable called found is equal to search 15. We don't have 15, so it should return false, right? Or let's say search is equal to this. So we want to search for 15 is the key. So we'll say print element. So let's say if search is true, we'll print out. So we search 15, right? So we'll print search is found, else print search was not found. Let's say search is not found. So let's try this and see if the search works. So when I run this, you say false is not found, and what we get here is false when we try to search there. All right, so we'll say true is found, false is not found. All right, but when we want to check for 20, for instance, we should have true is found. So you can see how we implement that. You can have more. Let's just play around with this. Let's say we want to get the length of the list, for instance, and we want this to be a method. So we'll say the length self, and we want to initialize a count to be 0, and we want to get the first item, current is equal to self.head, and we want to loop through. Let's say while current count is equal to count plus 1. So let's say count plus equal 1, and then we want to move to the next. So current is equal to current dot next, and then we want to return count at the end. And so when we want to get the length, now we can say length of list is equal to ll.length, and when we print the length of the list is length of list. So let's run this, and we have the length is 3 because what we have is 5, 10, 20. All right, so you see how we implemented the singly linked list. In the last lesson, we are going to look at what the doubly linked list and the circular linked list is, and we're going to try to see the implementation. So this should be like a trial for you to know how to implement this. You can implement it in a different way. You can think about different methods that you want to have in your implementation that will work with your use case, but this in summary is a linked list, and this is a singly linked list where we have the node contains the data and a pointer to the next. Thank you, and see you in the next lesson.